Should I start?
Yeah, it's all right.
Okay. Okay. Hello everyone. Good afternoon. First of all, I'd like to thank Professor Chetan for kindly giving me this opportunity to present my work. So today I'll be talking about inflationary models in string theory, like Professor said a few minutes ago. So in principle, I'm going to embed cosmological inflation, that is an era of accelerated exponential acceleration happened in the early universe, and I am going to embed that in a string theoretical construction, in particularly in type 2b string theory, where I will be interested in a particular geometry of the internal space, that is K3-fibred Calabi-Yau I will be considering. And first I will address the scalar field stabilization, because I will have a scalar field which is going to drive this accelerated expansion, the inflation. So first I will see if I can generate a potential for those scalar fields. Then after that I will see if it can inflate, so it can slowly roll and go to its minimum if we are interested in reheating to study further. And finally I will check the robustness of this well-known construction known as large volume scenario. So I will be starting from large volume scenario. It is a constructions to stabilize this scalar field. So it has been shown that the potential can be generated for the scalar fields if we study large volume scenario. I will be considering the perturbative part of it. So I will only add certain corrections, and then I will study inflationary models and check its robustness against addition of more corrections at the level of the potential. Okay, so this this talk will be based on these two papers. One of them is in JCAP, and all of them came out few months ago, and the other one is in PRD in revision, and this work is in collaboration with Swagata and Pramod from JC Bose and George from University of Ioannina. Okay, so in my talk in abundance you will hear these three things: inflation, that is a period of accelerated expansion, early period of accelerated expansion. Then I will be talking about large volume scenario. So what do I mean by that? So it means the volume of the internal space is large compared to other construction that was studied earlier. Not large compared to our 4-dimensional space, but large in the extra dimension. So the wave of the like vacuum expectation value of the one of the scalar field will be large in the extra dimension. Okay, and then I will be considering the corrections to this standard large volume scenario. So in large volume scenario what happens is you add certain quantum corrections, and there is a truncation to up to what order you want to go to derive your ultimate scalar potential. So I am going to go beyond the standard load, and I am going to check the robustness of such a construction and study inflationary model on top. Now this LVS, they have studied this standard Swiss cheese kind of internal space. So this is a 6-dimensional manifold. So it is like the way to visualize it, because we can't visualize 6D, right? So this is a way to visualize. So it has certain 2 cycles, 2 hollow, 2 internal cycles and some large cycles. And the way it is written is the volume of this total, the total 6D part is the large cycle minus this hollow cycles. And this hollow cycle is important because this actually gives rise to the non-perturbative effects, as well as it controls the non-perturbative effects. So that is the Swiss cheese Calabi-Yau, and we are going to deviate from that, and we will be talking about K3-fibred Calabi-Yau. And what is that? It is again a 6-dimensional space where I have a 2D base and I have a 4D base, and in both of them, in first case, I will be studying now 2 inflationary models. In one case, the 6D volume of the internal space is going to drive the accelerated expansion. It is going to be my scalar field. And in other case, this 4D volume is going to drive the accelerated expansion. So the K3-fibred. So why am I calling it a fiber? Because there is a circle, like it's a 2 cycle. It's a 2D manifold, a sub-manifold of the Kähler manifold. So it is a 2D, it's like a circle, and on each point of it there is a there is a 4D sphere. You can imagine like that. So on each point there is a 4D sphere, and this K3-fiber actually can stretch, and it can give us this accelerated expansion. So that is the K3-fibred Calabi-Yau, and again I repeat, so in one case, in one of the inflationary models, we will study the whole, where the whole 6D volume is going to drive the accelerated expansion, and in the next case, only this 4D volume will drive the accelerated expansion, known as the fibered modulus. And whenever I say modulus, it just means scalar field. So in the 60, it is a perturbation of the metric, and when I go down to 4D, so I will be talking about compactification very soon. So from 10D I will go to 4D. So in 4D there will be any scalar field, general scalar field, and since I will be interested in studying cosmology, so it will depend on time. The scalar field will be a function of time. It will have certain dynamics. Okay, so now I will be talking about inflation, right? So I better motivate why we need inflation in the first place. So inflation is an era of accelerated expansion in the early universe. Now why do we need it? Because we know there is a lambda CDM model of cosmology, the standard model of cosmology, which has 6 parameters, and using those 6 parameters, it can explain the observations quite well. It can fit the data more or less well, right? But it cannot explain why the temperature between two antipodal points in the CMB, this is cosmological microwave background, the 2D projection of the cosmological microwave background of the sky. So why the antipodal points have the same temperature? So just to explain that, suppose these 2 points, they are white, can you see that? Okay, so these 2 white points, those are 2 antipodal points. So if we consider like when this CMB was created, like at the time of decoupling, so when those CMB was created, and if these 2 points, if we interpolate towards the past, then we can see that the light cone, if we consider the light cone, then these 2 points were not in causal contact. Or in other words, if we consider the time of decoupling, then the largest horizon that we can think of to be in, between 2 particles, then that will subtend only the angle of 1 degree at the CMB. And if we consider 2 points which is 180 degree away from it, then they are not in causal contact, because 1 degree is my size, right? So that is the horizon problem, and so they are same but with an anisotropy of 10 to the minus 5. So they differ by 10 to the minus 5 if you consider any random points. Okay, so this is in conformal time versus space. So it is again conformally flat matrix, so that's why I can draw these light cones. So again I am stating the same thing. So these CMB photons, they are coming together in towards us for the first time. They are meeting for the first time on Earth, and then if we check at the time of decoupling, this is redshift. So at the time of decoupling, we can see that if we, after the time of decoupling, this point A and B, if we again interpolate back, then at the time of the Big Bang, that is the start of the time, we can say, so at the time of Big Bang, their light cone were not in touch, right? So now what does inflation do? So inflation actually further interpolates back to the finite redshift, not infinitely past, but at finite redshift z equal to 10 to the power 28, where the forward light cone and the backward light cone, they can be of the same size, so they can interact. Those 2 points, that A and B, or those antipodal points, they can talk to each other, they can interact with each other. So that's why we need this inflation. So this is an era, it is a framework, it is a paradigm, it is not a theory, so it is a paradigm. So inflation happens, so what is the duration of inflation? So inflation happened very early in the universe. Within 10 to the minus 33 to 10 to the minus 36 seconds, the universe has expanded by 10 to the power 25 order. Whatever it had started with, it has expanded to 10 to the power 25 order. Okay. So now this is the inflation, so we have to theoretically model it, right? So in order to theoretically model, this is an inflationary model. It is in its simplest form. So it is a canonical, I have a canonical scalar field and minimally coupled to gravity. So with the Einstein-Hilbert term, there is no coupling between with the scalar field. And it slowly rolls down in this potential. So this curve is one potential generated due to the coupling between the scalar field and others, or the scalar field within itself. So when it is slowly rolling, that's why the name is slow roll inflation. So when it is slowly rolling on the flat plateau of the potential, the inflation is taking place, and once it starts to go towards its minima, then inflation stops, because kinetic energy becomes greater than the potential energy. That is one of the conditions to stop inflation, because I need slowly rolling. So if the kinetic energy is greater than potential energy, then inflation stops. And how do we check all that? We check all these slow roll parameters. And this is a, in order to numerically code it or even do this analytical calculation, we need to solve 2 equations. So one is Hubble, coming from the Friedman equation, and the other one is this Klein-Gordon equation where phi is my scalar field which is doing this rolling. Okay, and we know that we are not in this inflationary regime anymore. So inflation has started because it can solve the horizon problem, and inflation has also stopped. So that stopping we will consider, we will categorize by these slow roll parameters. It is just taking care of the fact that the potential energy is actually dominant over the kinetic energy, or the Hubble parameter is almost constant. Okay, and on top of that, inflation does not only solve this horizon problem, it can also give it can generate the perturbation. So it can give the seed to the large scale structure that we see today. So we can also do perturbative, you can also do, study perturbation using this inflationary mechanism. And from this Planck data, so it gives certain constraint on the amplitude of that perturbation, then the scale invariance of the perturbation, the way it looks in the CMB, and also gives the amount of gravitational wave, primordial gravitational wave that can be generated during inflation. So all of them are bounded by this Planck data, and n phi is another very important quantity known as the number of e-folds. So number of e-folds means how much exponential growth has taken place during inflation, and that number is 60. So I was talking about exponential acceleration, right? So how much exponential acceleration has taken place, that is 60. And there is one important point is that the total amount of inflation could be greater than 60 as well. But what I mean by I need minimum 60, so 60 is the minimum number. It is the number between phi, so phi star is the start of inflation, so that's the initial condition, and then phi star is somewhere the largest mode has exited horizon that we probe in the CMB today. The K star, the pivot scale that usually people talk about when they give these numbers. And between that and the phi end is my total 60 amount of e-folds. Okay. Okay. Huh? Sorry? Yeah. Is the potential.
What's the form?
The form of the potential could be anything. So deriving the form of, a good question. So deriving the form of the potential is my goal. And people usually, so this picture that you see here, there are various potential has been plotted. I mean the model prediction has been plotted. So one of, I think this is natural inflation, this is alpha attractor, this is phi to the power 4 probably. So various, those are all toy models. So this V phi could be anything, any one of them. But deriving that form that we get from extra dimension, that is my goal. Some V, yes. Yeah. There are no constraints on V phi, but the model prediction, so what you are getting from the inflation, suppose, I mean, you have a V phi, certain V phi, then you do this numerical analysis or analytical approximation, analytical calculation, then the actual constraints will come from there. It's because they are all related, right? So using these and also other data sets, you constrain what will be the, not the form of V, but the certain model parameters in the V. Okay. Okay, so now, so this plot, what it is telling you is that single field models are in good agreement with the data, with the Planck data. So they are within this contours of 95% confidence level and 68% confidence level. So they are within that regime. So now what is the reason that we should talk about string inflation or go beyond single field model of inflation? You know, people also study multi-field inflation. I have also done some work on that. So the reason being, so this phi that I was talking about, the scalar field which is driving the accelerated expansion, so the origin of it is still an open question. So no one knows what is driving this accelerated expansion. We know some phi, so we just put it as an ad hoc. So what is the origin of that scalar field? So the string theory as a theory of let's not say everything, but it's a higher dimensional theory which has a certain topology, and those topological structure that can be embedded to this scalar field at 4D. So the size and the shape of this extra dimension can give rise to these scalar fields that is driving the accelerated expansion. So they have a physical origin coming down from a higher dimensional theory. Okay. And not only that, so we know in particle physics, in the standard model of particle physics, gravity is static. So we know that there is an unification of the three interactions, but gravity is static there. But at the level of when we study cosmology, we know that gravity cannot be static because gravity is a driving force there. So we need to have a theory where both gravity and other interactions of nature, including quantum mechanics, is there, because quantum mechanics we need to study those perturbations, right? So all of them together we need a theory which can give us those answers. So string theory is one of the leading candidates which can give so. So that's why, I mean, that is one of the reasons why we should be studying string inflation in the first place. And not only that, so this scalar field, I mean, it comes as a problem as well as a solution. So, when I do this compactification or when I get rid of this extra dimension, I do not get just one scalar field, but multiple scalar fields. So, and one has to make sure that those multiple scalar fields, except the lightest one, is stabilized. And what do I mean by that? Giving them a mass such that they are not dynamical during my cosmological inflation. So, there is no fluctuation, there is no, the dynamics is gone. Okay. And at the same time, they mediate fifth force. So, if they are massless and they are roaming freely, we would have been observed by now using this tabletop experience on fifth forces. So, they has to be stabilized, and this is the work of the string phenomenology or string compactification, string phenomenology. So, in order to, so what I am trying to do? So, I am trying to generate a potential for all these scalar fields. And it is not an easy task to do. I need to know what is happening in the internal space, how many ingredients I have to stabilize these scalar fields, and how do I compactify all of them and get a final potential which is de Sitter at the same time. So, it is not a very easy thing to do. I need to know some mathematics, some intricate structures. So, that is what I will talk about now. So, this is my potential. It is a quick trailer, like what kind of potential. So, you are talking about this potential, right. So, this is the kind of potential I will be working with, but do not look at each and every term, but I want you to look at the red ones, which are my scalar fields. So, I have three scalar fields, and volume, this the curly V, V total is the total potential energy, and curly V is my volume. And this volume is not independent of these three scalar fields, because these three scalars are dependent on this volume. So, I can just substitute one by the others. And I have three, I'm left with only three fields. So, these taus are my scalars, these taus, and the rest are stringy parameters, which depends on the construction I will be interested in. Okay.
So that tau is, so V, the V is the
volume of the internal space.
It's a function of the taus also.
A function of the taus also. So, it's actually this. So, V, curly V is square root tau 1, tau 2, tau 3, and all of them has dimension less to the power 4. So, 3 times 4 square root 6, dimension 6.
That is in the specific model that you...
Yes, yeah, it is like toroidal like volume here, and those are 4 cycles, these taus are 4 cycles basically. Okay. And after some canonical transformation, so after some base transformation from tau 1 to phi 1, phi 2, phi 3, I can finally arrive at this.
The coefficients that you had, are they, what you think of them as complex structure moduli or something? What are the stabilized things? This looks like there is only K1 moduli.
Yeah.
So what happened to the others?
Right. So, the other what happens is that, so this moduli stabilization is a 3-step process. First, I use this tree level superpotential and Kähler potential. I stabilize my axiodilaton and the complex structure, and then their wave is encoded in this W0. So, the wave, I mean the constant part of the superpotential.
So your point, I guess, is that this is the part that contributes to the inflaton. Is that what you're saying?
Yes. And why I can say that? Because the others, the complex structure and the axiodilaton, they are heavier. So, they are integrated out. And in the second, so that is the first part, I stabilize those two moduli. Then I look at what is left. So, I check the Kähler moduli part of the scalar potential, and I see there is 0. So, there is nothing there. So, I have to add at that point perturbative and non-perturbative correction. I generate potential, and then I uplift. I'll explain all that. So, this is the simplest, not the simplest, let's not just say simplest, but a simpler looking potential compared to the previous one, where here this phi is a total volume of the internal space, is the total 6D volume, and in the second one it is a 4D volume. So it is one of these 4 cycles that is driving the accelerated expansion. This is fiber inflation, this is the volume inflation, and both of them has this nice flat plateau where it can roll down and give us enough e-folds, and I will explain all that. Okay, and this is single field. At this point, this is single field, and why I can do that, I will show you. It's just checking their mass spectrum. So I have integrated out again the massive ones. I am only working with the massless, I mean the less massive one. Okay. Sorry? I will show you, yes. I think, I should just put it at this point, maybe everyone is confused by this. So I have put all of them in the like later slides, it will become clear. Oh, X is actually, yeah. So X is taking care of the uplifting. So I will explain all that. So that's why it's a quick trailer, like, so what we are getting into. So I will explain all that. So,
what X? I didn't even see any X.
Oh, this one. And here I don't have it, but here it is taking care of how much anti-de Sitter space I have and how much I need to uplift to get a de Sitter. And why do I need that? So for inflation, a priori I don't need a de Sitter because I just need enough e-folds, but to study reheating and further processes, maybe to quintessence maybe, I need a positive potential or like a positive potential, let's just say. Okay, so this is string compactification in a nutshell. So what do we have here? So we have this 4D, which is our 4-dimensional space-time. Then on top of that, I have 6 spatial dimension. So that constructs this 4 plus 6 10-dimensional superstring theory. Then on top of it, one can truncate that right there. So that is a superstring theory. And then if we also have this plus 16 spatial dimensions, that is the bosonic string theory. And why it is not very useful? Because it does not include the fermion. So it does not have the chirality. So one usually interested in this 10-dimensional superstring theory, and upon quantization it gives rise to this 5 types of string, like 5 types of string theory, and one of them is type 2b, which I will be interested in, because in type 2b the moduli stabilization is the most it's the most studied one. Okay, and this 10-dimensional theory, it has certain, so in 10D what happens is, in the 6D the internal space, how it looks, we don't know. We only approximate it. So we don't know the exact metric of this internal space. GMN we don't know, small m, small n. But what we know is there are certain, the topology of it we know. And that is one of the important thing, because using that I can see how many moduli or scalar field I can turn on. So how many moduli I can turn on, how many scalar moduli, complex structure, accelerator, accelerator is just one, how many complex structure and the scalar moduli I can have in the internal space. And those are actually imprinted once I dimensionally reduce. So the size and shape of the extra dimension, those are the moduli, those are the field driving accelerated expansion. So once I stabilize them, I know what will be my corresponding volume of the internal space. And the size of size is the complex structure, which I am not talking about right now. Okay, then so this is, so yeah. 1, 2, 3, 4, 5, 6 type. So there is type 1, type 2b, type 2a. So if you just consider type 2, then maybe you are.
Yeah, but I thought, so those are dualities or something, right?
Yeah, they are all related through certain dualities. Yes.
What theory did you say you?
No, the vertices, the corners of the vertices are theories that are related by dualities, right?
Yes, yes, yeah.
The connection is not immediately direct. So it can be through its absolute attachments or the T duality.
T duality, S duality, R duality. Yeah.
It's nothing to do with it.
Okay. 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 Yeah. So the number of, so like I said, I need to know the topology of the internal space, and that I can consider, that I can construct using this Betti number. So this H11, H12, that is just telling me how many scalar moduli, how many complex structure moduli are present in my internal space, my extra dimension. Okay. So this is the rest of the talk. I will be talking about the moduli stabilization. So all this scalar moduli and the complex structure moduli, so H11 and H12 numbers that you can see. So I am going to address the stabilization of that. So what do I mean by stabilization? Giving them mass, right? Giving them a non-zero, non-trivial potential. and then I will be trying to search if I can have a de Sitter vacuum, and I have already shown you yes, we can, and then I will be checking their in cosmological implication and its robustness against addition of more corrections in the perturbative and non-perturbative series actually in my case. So this is the standard prescription what you were asking. So I have this superpotential, scalar potential. So superpotential is a function of only the axial dilaton and the complex structure at the tree level. So that is the simplest Feynman diagram that one can draw at the level of string wall sheet theory. And this is the scalar potential which depends on all the three moduli. So S is the axial dilaton. Then omega is my complex structure and V is the volume which is the scalar moduli. So scalar moduli is the overall volume. It denotes, it takes care of the overall volume of the internal space. Okay. And this is the final form, I mean this is a formula to write down the overall scalar potential in the end. Now if you look closely, so if you just write down the scalar potential, so if you take a derivative, because it has a certain derivatives, right, covariant derivatives. So if you compute all that, then you can see that if you compute this term from here and if you plug in this KTT, this V of Ft, so the scalar potential for the scalar moduli, it becomes 0 at the tree level. So that's why we need to add more corrections so that it does not, it is not 0 anymore. So I add more corrections at the level of the potential or at the level of the scalar potential or the super potential, because they are all interrelated. So I will do that and I will generate a non-trivial potential for the scalar moduli, and that's what I am interested in my work, and one of the moduli to be driving the accelerated expansion. Okay, so again, so I will add quantum correction. So this is, suppose this is a.
It would be useful for the students if you spend a bit of time on the slide before this one, because I want this one. So where, so for instance, I mean, there are a few facts which are very universally used, and I think probably none of them have heard about it. So I think if you say a few words about that.
Okay, this.
I mean, just I'm not even asking you to really derive it, but just explain that it's going to go off on the standards.
Okay.
A few words about that, I think you just.
Okay. So this is the standard, again what Professor just said, it is a standard Gukov-Vafa-Witten superpotential. So it is a dimension, mass dimension cube. It is a mass dimension cube. So,
so what I was just saying that, like if you start from a high dimensional theory, you get, so a low dimensional theory is basically defined essentially just completely by the scalar potential and superpotential. That's a basic fact that if you just say that, I think a lot of the mystery is gone.
Okay.
So, and if you have the scalar potential and superpotential, then the actual scalar potential of the theory, which is the last thing that you've written, and that is completely determined.
Yes.
So if you know K0 and the K and W,
the scalar potential is determined.
You are basically trying to construct this potential so that whatever scalars are there in the potential, which is multidimensional, it will all be trapped in somewhere. So that's what you're trying to do.
Exactly.
So I think that from the higher dimensional point of view, string theory basically gives you these specific choices for K0 and W. So that's the first line is the superpotential.
Yes.
And this I think is a motivated for Ferrara and company, right? So this is a K0.
Yes, I get so. Yeah.
So those are the results of dimensional reduction. This is the specific form.
Correct.
I'm just talking
Correct. I mean it's helpful.
But so these two things you get from dimensional reduction, and that form, if you plug it in, the statement is that there exists a class of scalars, which are these scalar moduli, which do not get trapped in this VF. They have a flat direction. That is the problem. So that, which means that the size of these compact manifolds can become decompact. So that's really the problem that she's talking about.
Exactly. And so thank you so much. And those scalars are actually, I mean, if I do not add certain extra corrections, so those scalars are the scalar moduli. So what I want to study at their potential, so those are actually flat at the tree level. So by tree level I mean just this order. So K0 and W0 is the first order.
I would say that this is sort of the most, this is the main slide for the picture that she's going to talk about. So, and I think the ingredients are these higher things. So, omega-3, for instance, is every Calabi-Manifold has a thing called a 3-0 form.
3-0
form,
that's a
property of the Calabi manifold. So, that omega-3 is there, and G3 is some flux in the 10 dimensions that is there in
Yeah.
theory.
From type 2 string theory,
So,
yeah, is a
given
G3.
those three things, if you dimension reduce on a Calabi-Yau threefold, Bukov and Wafra and Newton basically say that you will get a universal superpotential, and that's that expression.
Yeah.
Okay, so that's the first line. And the second thing is, again, it's a dimension reduction to 4 dimensions is always hard, but this is an explicit result that you get, and the S basically contains the axion and the dilaton of string theory, and omega 3 is again the Calabi-Yau three form, and the V is basically the volume of the Calabi-Yau. Okay, so these three things together give you the Kähler potential. So that's the statement, and the Kähler potential and superpotential are standard structures that exist in supergravity in 4 dimensions. And once you, that's in a certain way of writing. And then the final statement is basically that the scalars in the theory will need potentials. This Vf that she is writing is the actual potential in the Lagrangian.
Yes.
So that Lagrangian potential is determined in terms of K0 and L, not in terms of this particular formula. So these are all standard facts, and I think it is good to kind of remember them. If you otherwise, so if you remember them, I think many of these things will be quite transparent. Any questions anybody has?
And see what
most of them are my students,
yes, of course, yeah.
So I told them to come to the talk.
Yes. And
from the superpotential, they are getting some real potential that get added.
That's right.
Yes.
See, Kähler potential and superpotential are basically ingredients in a supersymmetric theory. And then at the end, when the dust settles in supersymmetric theory, basically just as an ordinary Lagrangian, right? And that Lagrangian has a potential term for the scalars, and that's the last one. So,
yeah, and just look what I am doing. So I said that I will be stabilizing two of the moduli, which is complex structure and the axial dilaton. So that I am just doing by using just taking the first derivative of the scalar potential and just like putting them to 0. And then I plug that back in to the overall potential, and that's what I mean by integrating them out. So I am giving their wave to the scalar potential. So after doing that, I will add the quantum corrections, and I will make one of the scalar field to be dynamical. So and then I will study, using that I will study the inflationary models. Is that clearer now? What is? Oh, exponential k is just that. So k, and so this k will not only be just k0, but all the corrections that I will be adding to stabilize this one of the field that was flat, that is flat at the tree level. Tree level k naught.
So there are corrections coming from all the string theory has lots of corrections. So and I think so the point is that without including the corrections, you basically are not able to stabilize. So this potential with this particular reduction structure has a property that the Kähler moduli are just not stabilized.
Yeah.
So they don't have any, they're flat.
Exactly.
They have directions.
Yeah.
So those directions are called flat.
Flat direction. So the potential will not be generated, and it will just be so this is what I mean by flat direction, like there is a runway. So there is no stabilization, there is no minima for those in those directions. Any more questions? Yeah, please feel free to ask me any question.
Yeah. So also because it's student, you guys should be just free.
Yeah.
Except for me, none of the faculty.
No, he is there.
No, but he's not strict.
Yeah.
He's not judging us.
Yes. Okay. And so once first I should say that. So once I derive this scalar potential after the addition of the quantum corrections, I will get a ADS minimum. Then I uplift using some other ingredients, and then on top of it I will have this scalar field which was flat at tree level. Now I have a potential generated for it. Then I will displace it from its minima, and I will let it roll down towards the minima, giving us the exponential acceleration, the 60 folds. Remember what I was saying, this flat plateau, and then there was this minima. It has to roll down certain distance and giving us this 60 folds. So that's what's happened. That's what will happen in this potential, the potential that I showed earlier. These three fields. Remember? What? Which one? This one? Okay, so this is 0. This is a cartoon, by the way. This is what the KKLT looks like though, but yeah, this is a cartoon. I will show you. Potential is negative. It is 0. Yeah, potential is negative. That's what I mean by ADS. Yeah, and then I uplift. I get a de Sitter potential. The minima of the potential is positive. And then I will uplift, and I will have one scalar field displaced from it. Oh, yeah. Okay. So this is the 10-dimensional type 2b supergravity action. This is the action where I am adding all these ingredients that will be helpful to state to write, I mean all this superpotential and the scalar potential that you see, that you saw earlier. So all those are coming from this extra dimension, right, this 10-dimensional supergravity theory. So all of them are encoded in this first line. And then on top of that, so this is what I mean by perturbative expansion, perturbative series. So the in perturbative series in string theory, we take two perturbative expansion in string theory on top of this type 2b action. So one is an inverse string action and the other one is the string coupling. String coupling is the how this one string is interacting with the other one, and usually in order to apply this semi-classical supergravity approximation or to work in this 10D supergravity, we need to be a classical regime where I have large volume and weak coupling. So, and we take the expansion in both weak coupling and this, so I am not showing the weak coupling one, I am just showing you this alpha prime expansion. So, which log? Oh, LOC is a local correction, so it is where the D branes and the local terms, the non-perturbative objects, they sit. That is. There are D7 branes that will yes, yes. Yeah. Okay. So now I will be mostly interested in this alpha prime. That is the first non-trivial correction that one can add. So that is the alpha prime cube correction. And once you add that and also add one non-perturbative effects at the level of the superpotential, there will also just be, oh, I will have that. So yeah, once I have this, so this is the alpha prime cube correction. This is how it looks like. This is how it modifies the, remember I was showing you the K0. So this is how it modifies the K0. So there will be an extra correction where GS is a string loop. And this, once I add the non-perturbative effect, this is the non-perturbative effects. So it is exponential minus AITI, and Ti is the size of this internal space, size of the internal cycle, hollow cycle, which can be, which has like 0 volume. So which if it expands, it reduces the volume. Okay, and this is the total volume, and this is the potential generated for the standard large volume scenario. And why is this large volume? Because there is this exponential at the vacuum expectation value of the overall volume. So this exponential is sitting there, and it comes directly from minimizing this potential. So these are these two parameters that is stabilized using the standard large volume scenario.
So what is what is tau L and tau S? Oh.
So large cycle and the small cycle.
So the large cycle is the one that basically becomes
the volume, making the volume. Yeah.
So that's why it's getting.
Yeah, no. So Ti is not, so that is a catch. So Ti is not the large cycle. Ti is the small cycle. Why? Because I need to make the non-perturbative series under control. So Ti is the smallest cycle among all these small cycles that is there in my.
So the what was psi here? You can remind me what psi was at the top.
Psi, oh, this psi, so that depends on the Euler characteristics of the internal space, which is written as, which also depends on the number of scalar moduli and the complex structure moduli you have. Some detail of the Calabi-Yau, geometry of the Calabi-Yau.
Capital AI and small a are what? That's also
those are the
also geometric fact.
Yes, they are the Pfaffian. So they are telling you the amplitude of the non-perturbative effects. That is a constant, but it depends on the complex structure moduli and the axial dilaton. And in our case, I will treat it as a constant because I have already considered that the complex structure moduli and the axial dilaton are integrated out. They are heavy. So I have already stabilized them at the tree level, and they are in the W0. This is W0 actually. So they are in the W0. Is that clear or
so somehow that value you treat as a constant?
Constant, yes.
It's fixed by the first term.
Yeah.
And so where is this? V is going in the tau L and tau S. And so this expectation value that you are writing down is basically just
taking derivative.
This term is basically the result of doing the computing the potential from all this complicated stuff.
Yes.
That supergravity formula. And then you are looking at the expectation value of the actual volume, just computing.
Taking the derivative of the potential dV d capital V d is curly V.
Okay.
Yeah.
And the claim is that that is somehow determined by the tau S.
Tau S, the smallest internal cycle. Yeah. And even, I mean, by small, I mean it still has some amount 2 or 3 or 4 order 1 parameter, and even the order 1 parameter, exponential order 1 parameter is huge. So that's how I get this exponential large volume scenario, exponentially large volume.
So and so in some sense it becomes self-consistent to use supergravity.
Yes, yes, absolutely.
So when you go back to the previous slide,
Yes. You mean?
because there, in your thing you were doing the corrections with alpha 3. So what happened with alpha 1 and alpha 2?
Oh, so alpha 1 and alpha 2, they become 0. So first non-trivial correction starts from alpha prime cube. Okay.
So that is the correction of vector and some curve.
Yeah, BBHL term. Yes, yes.
And the genus remains at 0. There is no genus expansion.
So genus expansion, I mean at this BBHL, so alpha prime cube, genus expansion is 0, but you can also consider this loop corrections. Yeah, I will be considering them actually. So these are the series of corrections I will be considering. So I will not consider this in particular, but this is sourced via this genus corrections, so the loop corrections. Yeah, and I will not consider, but these are the corrections that is possible. Those are possible corrections that you can add to have VFT non-zero, because you remember that those were my goals, right? So in order to have VFT non-zero, these are the list of corrections I can add, but I will be considering these 3 corrections as well as this winding one loop open string corrections. Okay, so and these are the list of corrections I am going to add, and this is how it is changing the tree level Kähler potential. And Kähler potential, and these are just the addition of, I mean there are obviously.
What do you mean by log loop corrections?
So log loop corrections are okay. So, okay, I can just say that. Okay, so log loop corrections, it happens at the level of the alpha, I think it is one of the higher derivative corrections. So it takes place at alpha prime cube r to the power 4 order, and it gives the correction is written in such a way so that it gets a logarithm term. The logarithm term is generated, and eta is again depends on some
Why is it some alpha prime corrections?
Some alpha prime corrections, yeah, high derivative corrections, yeah, alpha prime corrections, and it contributes to the Kähler potential, yeah, and it just means that log, so logarithm term is there, yeah. Okay, I also have a slide. I mean, in the end, I can show you exactly how it comes up. Okay, so this is what I mean by from large volume scenario, I'm going to a global embedding of that. So I will have a master formula where I have all the perturbative, I mean not all of them, but more perturbative corrections added to the overall scalar potential, and from there I will derive my single field inflationary model, and I will check what is the robustness of it, because previously people added only 1 or 2 corrections. I will be adding more corrections and checking the robustness of the inflationary models. Okay, I have already said the other one. So this is the standard LVS. Now I will not consider this type of volume form as well as no non-perturbative effects. Instead, I will be adding this perturbative corrections, and I will be working in a particular volume which looks like this. This is the volume form, like the form of the volume, the formula of the volume I will be interested in. And again I can see that without the use of any non-perturbative effects, because you remember in the previous case the non-perturbative effects was just sitting in the wave of the volume, exponentially tau s. Tau s was sourced by these non-perturbative effects.
See, this is the thing that always worries me about this kind of concept, because
Yes.
like in the original LVS construction first they just completely ignored this term essentially.
In the LVS construction, yeah.
So which means that they came to some conclusion. And and then now you add this and you say that you can also get this as well here.
Yeah.
So at what point do we decide that we have incorporated all the relevant corrections?
Yeah, so yeah, it's still an open question. Yes, like at what point I truncate the series, right?
Yeah,
Yes.
because it is like it's not clear that like I mean, there are multiple expansions.
Yeah.
There's always a question of whether we
Yeah.
have incorporated
All the relevant corrections, yeah.
Because there are so many fields.
Yeah, so but what happens is they are always subleading to it, right? So here,
Yeah, but I mean, subleading means, but you kind of have to do a calculation to see which ones are relevant.
relevant, yeah, that is also true, exactly. I mean, that's why it's still an open question, yeah. So we have gone beyond certain order, and we have checked like if they have some effect in our inflationary model, and they do have some effect in the inflationary model. I mean, I cannot ignore their effects. I should not ignore their effects. Okay. So my point was that even not adding any non-perturbative effects, I can still get this exponentially large volume with the help of weak string coupling. So if I have GS 0.2, I can have large volume, exponentially large volume, and so this, and for even 0.1. Okay. Oh, and at the level of the potential, once I stabilize, once I plug this V mean back in the potential, I will have a negative potential because eta is negative. It depends on the geometry of the internal space. It is negative. It has been shown it is negative. So, I need to uplift, and I will uplift using this d terms. Using this term, I will this 1 over tau to the power cube term, I will uplift to a de Sitter potential. And so, I think you were asking like how this phi is related to tau. So, this is the canonical transformation I will be adding, and why am I interested in canonical? Because canonical canonical transformation, it simplifies the calculation, it simplifies our life in the sense that I can directly get their mass from the double derivative of the potential without having to worry about the metric. And
so under this transformation, the kinetic term becomes canonical.
Yes, yes. Yeah. Okay. And also the potential becomes simpler looking potential.
So with this eta, the potential was negative. They added this term.
Yeah.
And got to the uplift.
Yes. Yeah. Okay. And these are the, so there are certain constraints. I mean, I'm going to a single field model, right? From I have started with 3 field. So there are certain constraints imposed on my scalar potential or the way the scalars should behave. One of them is that the one that I want to inflate with, that is the less massive one. So the others, I mean, the mass of that scalar field has to be smaller than the other two. So that is this constraints, and these constraints arise because we also want to have this. So this again, I mean, these constraints arise from this hierarchy. That is, one of the scalar field is actually less than the others. So like the other two, and at the same time, this minima is positive. So one constraint is coming from there, and these constraints will become relevant when I'll be putting some values to all of them. I'll be plugging some value of W0, GS. And I will derive this A1, A2 and all of them. Okay. And this X, who was asking about X? Yeah. So, this X is taking care of the uplift. So, the D term, so this D term will contribute to the overall potential, and the contribution of that will be encoded in this small x, which is a constant. No, not at all. There are various other ways. D brain, anti-D3 brain uplifting is there, then T brain uplifting is there. So this is D term uplift. This is just one of them. Okay, right. And after addition, so we have a de Sitter potential at this point. I have added the D term uplifting, and these are my minima, maxima, and the inflection points in the potential, and it looks like this. Right, and so it has a nice flat plateau where it can roll down, and this is the overall potential where I have just one field, and I have added just 2 corrections, that is alpha prime cube correction and the log loop corrections and the D terms. Okay, and these are the parameters. So once I plug in the parameters, so these are my model prediction. So I have this NS and NS correct value. V is largish, 1000, not 10 to the 4 order, but 1000. So this is one of the benchmark model. I mean, this is the best model that we can find, and I mean, it is also satisfying the observational data. So we are happy with it. Okay. So now we will check the robustness of the previous model against addition of more correction, that is this winding loop corrections as well as the higher derivative corrections, and also the presence of the D terms. And this is that potential written in the simplest form possible, simpler form, and this phi is my scalar field, which is the overall 6D volume. Remember, I was talking about 2 different inflationary models, right? One was volume inflation, the other one was fiber inflation. So one is 6D volume, the other one was the 4D part of the total 6D volume, right? So this is the 6D volume part. So this is the overall volume phi. Remember, it is related to V as this. So, and I have removed the phi 1. So this is phi 1. The final potential that you see is phi 1, and it is related to the overall volume. Okay. So I am checking the robustness now, and so these are all stringy parameters. So all these constants that you can see, they all depend on the string coupling, and this C, you can see certain C, the CW is a constant that we can choose, because once I add all these corrections, it has been shown by various authors that those corrections, the value of those coefficients sitting in front of those corrections, they can be smaller, they can be naturally small. So that's why, I mean, we have certain freedom to choose that as small as possible and as small as we need to match the data. And like having done all that, so we have this potential, several potential for different values of R1 and R1 and R2, and this R1 or R2 is just taking ratio between C2, C3 with B. Okay. And so for one of them it is not possible, we have shown, and for others it has a nice potential, it has a minima and the maxima and the inflection point. The inflation can start close to the inflection point and roll down to the minima, giving us the enough e-folds, the 60 e-folds that I was talking about in the beginning. And these are again the model parameters. We have checked the hierarchy is intact, so the field driving inflation is the less massive one compared to the other two. And I have the volume is okay. So once I add all these corrections, the volume is slightly lesser than the previous one, so 1001. But this, okay, yeah, vary the parameters. So the actual checking of the robustness will be, I mean, according to me, that I have these parameters, right? So I have added, I mean, I have these parameters. So in the ideal scenario, I will have this same parameter space, and after the addition of these two terms, I will just vary those two and I will check the robustness of the original inflationary model. So we have seen that was, I mean, I can get certain, I mean, I can have inflation, but the model prediction is not good. So NS and R and the PS is not matching. So for that, what we have to do, we have to change the whole parameter space. But what I want to say is that the inflation can still happen after the addition of all those corrections. So that's how it is robust. The inflation can still take place even after adding, even after changing the overall potential. I mean, starting from tree level, then addition of certain corrections, addition of even further more corrections, going like subleading order, going to subleading order, inflation can still take place and it can match the observation.
But these parameters will change.
These parameters, yeah, they have already changed. Yes, yes. Okay, and again, this N, sorry, there has to be a dot. NS is 0.96, R is small, and then PS is, it's matching the data, it's 10 to the minus 9 order. And so this volume inflation is a small field inflation, which is important. So that's why my R, the value of R, the spectral tilt is small, because it is related to the light bound. And at the same time, if we consider this swampland distance conjecture, so it is satisfying that, I mean, if we believe on those conjectures. Okay, so now, so this is the volume inflation part. So how long do I have? I think I have already crossed the time, or I don't know. No? Okay. Okay, good. Okay, so this is the fiber inflationary part. So I just have like 3-4 slides left. So this, okay, good. Okay. So this is the fiber inflation part where the volume form will change. The volume form is slightly different than the other. So this is the standard fiber inflation where I have 3 Kähler moduli. And so these 3 Kähler moduli, so they have different role to play. So one of them is taking care of the volume of the base, the other one is taking care of volume of the K3 fiber, and the third one is taking care that the overall volume, it is taking care of the overall volume, and it is making sure that if you are interested in studying inflationary model, that volume does not change. So the volume remains constant, it's still a large volume scenario, it still has a large volume. Okay, and this is the type of potential that people usually use to study the fiber inflation, and in our case we will go slightly away from it and we will consider this type of overall volume, and we have 4 Kähler moduli, so tau s and tau 1, tau 2, tau 3, and then after addition of the same set of corrections like I was talking about before, I am arriving at this potential which is again written in terms of one single field, which is the fiber modulus, which is the volume of the K3 fibered Calabi-Yau, the subset of the overall Calabi-Yau, and this is my overall potential, and this phi is that K3 fibered Calabi-Yau. And this, all these CR part 0 R1, they depend on the stringy parameters, stringy details again, and we can fix it by fixing the GS W0, what I will show you now. sorry, yeah. So I will fix all these W0 and all these parameters, and then those parameters can be fixed. And again, after fixing all that, I have the enough e-folds. So N star is 50, which means the minimum number of e-folds 50 was achieved. And PS is again 10 to the minus 9, NS has the correct value, and R is slightly large because it is a large field inflation. In fiber inflation, I have a large field inflation. And in our, so again, so plotting those potentials, we have seen that we have enough number of e-folds, it is flat enough, and it can satisfy the data as well. It is within the Planck contour. And one of the important point about this large field inflation and fiber inflation is that considering this type of Calabi-Yau, considering this type of volume as well as the perturbative LVS, studying perturbative LVS, it has relaxed the bound on the total field excursion that was originally there in the fiber inflation. So in our case, there is no bound on the how much the field can move. So that constraint was uplifted in our case, in our fiber inflation model.
So but that is something that you find from the actual evolution?
No, that was in the, because we do not have a non-perturbative effects, that was found in the extra dimension. So it is the extra dimensional theory. So it comes from the Kähler cone condition.
What is 5 star here?
5 star is a pivot scale. So that is where the largest mode has exited the horizon. So that is the point I will be calculating all that.
Okay. So in order to get this much inflation, basically how much does your scalar field have to move?
So it depends on the model, first of all. So in our case, I mean, I don't remember. So see, 5 star is 6.22 and phi n is 0.92. So 5 star will be slightly larger than that because I am starting from the right hand side. So from right hand side, I am trying to roll down. So if phi star is 6.22, that is where the minimum.
All these are in Planck units, right?
Planck units, yeah.
So what is so from this picture here, it looks like the evolution that you have is, I mean, okay, this is large field, I guess, but so it is trans-Planckian, right? Basically.
Trans-Planckian, yeah, absolutely, yes.
So, but in general, I mean, but you know, I would say that that's one of the more maybe trustable small Planck conjectures, in the sense that if you have a order 1 field movement, you know, generally speaking, people expect that black holes will form and so on and so forth. So like it's kind of like it's typically in string theory, whenever a scalar moves by order 1, you kind of have to go to some development. So in that sense, I mean, I don't know, I mean, I like from the other one that you had in the small field model seemed more,
yeah,
like, I mean, you know.
Yeah, that is true. So that is a Swampland distance conjecture. So it depends on, so this mass of this, so mass of the tower of the light fields, it depends on exponential minus some scale times the wave of the, the total field excursion. This is some scale, and the del phi is the wave of the, the field excursion, the total amount of distance the field has moved. So if this is trans-Planckian, which is like if this is greater than 1, then it just, that makes them, the modes even less massive, it makes them light. There is a tower of light states appearing, and you have to incorporate them in the Lagrangian.
Yeah, because the effective field theory has changed.
Yeah, the effective field theory has changed. Okay. So yeah, I'll just conclude. Okay, so today I have shown you 2 inflationary models, where one of them, where the overall volume was driving the accelerated expansion, and in the second case, the 4D volume was driving the accelerated expansion. Hence, the second one is the fiber inflation, the first one is the volume inflation, and in both of the case, we were interested in only the perturbative regime of the overall, like we were interested in perturbative regime to stabilize this volume, either the 4D volume or the 6D volume, to an exponentially large value. So to trust our underlying effective field theory. Okay, and then we have found that the fiber inflation is a small field inflation, and the volume inflation is the other way around. The volume inflation is the small field inflation, and the fiber inflation is the large field inflation. But in our construction, the overall excursion of the field space is not bounded because of the absence of the non-perturbative effects. And after the addition of certain corrections, we have also checked the robustness of both the inflationary models, and we can see that inflation still works. It can give rise to the data correctly, and yes, so that's all from my side. Yeah, thank you.
So somehow your model, so your the superpotential is just the tree level.
So superpotential is the tree level one. Yeah. So the non-perturbative part only adds to the, all the corrections are coming to the Kähler part.
Yeah.
Yeah.
So the perturbative corrections in the scalar potential are enough to get everything.
Yeah.
That's the statement.
That's a statement. And I mean, constant W0 is there, but
constant
yeah.
W0, but I think is there.
Yeah.
So, okay. So in KKLT, for instance, they would try to make W0 very small and then match it with the non-perturbative thing.
Yes. So in KKLT, the volume, I think it depends on ln 1 over W0, and that's why they need W0 to be very small. I mean, if I have written it correctly, I think not volume, but the tau, the one of the tau.
Basically,
one of the
W0 has to be such that it can be comparable to the non-perturbative.
Yes. Yeah. Yes. Oh, why do I? Oh, for inflation, right? So during inflation, we have seen. I mean, one can see that the other fields, if you consider the vector and the tensor, they dilute away faster. So this scalar also dilutes away. So they depends on this. One of them is 1 over a cube. So scalar field dilutes away as 1 over a cube. A is the expansion, the amount of the scale factor. So it is taking care of the amount of expansion you can have in the space time in all direction, homogeneously and isotropically. And for vector and tensor, they dilute away even faster. So in order to study the perturbation and even the to study the dynamics of the scalar field, you need to choose the scalar field. You need to choose the scalar field.
But I mean, there are some models where I think
there are
these gauge inflation models and all that. See, I think the primary reason why people do this is because in string theory there are so many scalars. So that naturally, if you dimensional reduce, you get so many scalars, and if you can get potentials for those scalars, then it's, string theory somehow naturally seems to be friendly to inflation in that superficial sense, because there are lots of scalars in the theory when you go to 4 dimensions. The only question is how do you, get all the constraints that you want, then it becomes.
I mean, it can also have some tensor, right? I mean, it can not only tensor but vectors.
The scalars are the one which are potentials.
Yes. I mean, unless you tweak the 4D Lagrangian, yeah.
I mean, even if in just any theory, I mean, the vacuum structure generally we believe is controlled by scalars. I mean, very roughly.
Okay.
I mean, I mean, the moment you are trusting your classical equations, I would say that you are believing that your scalar field is the one that is.
Okay.
Otherwise, it would be like something like you see.
Okay. Yeah. Right. So this scalar, I mean, you can visualize them actually. So we write down this GMN, which is our 10D metric. This is 10D. So this directly from this 10D you can get all this scalar and tensor. So this is a tensor. This is the metric of the 4D. This is 4D. Then you have this G mu m. You have this G nu m n. Sorry, n, and you have this GMN. So these are the scalar. These are the 6D scalar. These are the 6D scalar. And these are these are vectors, and this is the tensor, the 4D metric. And you can directly separate out the 4D scalar and 6D scalar and tensors and all that.
Okay. That's like.